let me just give you a quick topic. We are going to look at estimating the difference in two means. So I'll give you a little bit of the background and the theory, and then take you straight over to the homework, because all of this section is all done by Salt. There's no way in the world you could do this by hand, right? The math of it would be ridiculous. You'd spend, 2 hours doing a question if you had to do it by hand. So I want you to imagine that you have two populations now. So the problem has got twice as complicated. Right? Population one, let's say it's females. And let's say we have another one, population two. And let's say it's males. And we would be interested in the difference between the two population means. So I don't really want to know what the mean of this one is or the mean of that one. What I really am interested in is what's the difference between them, right? Now, let's suppose then that I think that women have an IQ that's larger than men's, right? That way I won't get into trouble by being sexist. Strangely enough, as long as you say women are cleverer than men, it's not sexist. If I'd said men were cleverer than women, I would get into trouble. Do you see the unfairness in that? Anyway, so I can keep out of trouble, although that last sentence probably got me back into trouble. Females, I think their IQ is higher than males. So I collect a sample of 100 females, and we find out that their average IQ is 103, right? And that their standard deviation was 5. And then I get a sample of males. It could be 100, but let's just say that the way the money worked out, I managed to get 200 of them. And the IQ for these guys is only 101, and the standard deviation would say 3, right? What we're trying to estimate here is the difference between the two means. So we could do a 90, a 95%, or we could do a 99% confidence interval. And because what we're saying is what it is, there's probably going to be an 80% are floating around, and we're just going to laugh at them, but do it anyway, right? So these are the three that we should be doing, but occasionally they throw that one in. And let's just pretend that I found that the difference between the two was negative 4.1 up to negative 2.1. Can you imagine that's what I got? Oops, wrong way around. Plus, But the difference that to that would be big, right? So let's say the difference was 3.1 up to 4.1. Now, what that is telling us is that the difference between them is somewhere between 3 and 4 points. Okay, that's how you would interpret that. Now, aren't all of those positive numbers, right? Every single one of those is positive. So you're telling me that the difference between females 1 and males 2 is positive. Agreed? That's what that interval is saying. And if you rearrange that, isn't that logical conclusion then that you've now shown that women have a higher IQ than men? Does that make sense? If the interval has nothing but positive numbers in it, then the first population has an average that's bigger than the second population. Now, a totally different story. Suppose I got an interval that looked like that. Then since all these numbers are negative, doesn't that mean that the difference between the first and second population is a negative number? Right? And the conclusion to that then is that wouldn't this interval would be evidence that the first population had a smaller mean than the second. So you're going to get an interval where they're all positive. Your conclusion will be the first population mean is bigger than the second. If you get an interval that's all negative, won't your conclusion be the opposite of that? The first population mean is less than the second. And you might get that. That's the third possibility. Now, in this third situation, do you see that there are negative numbers and there are positive? So couldn't the difference be a negative amount, it could be a positive amount, couldn't even be zero, which means that they're both identical, right? If you get an interval like that, York will say that there's no conclusion possible. It means we don't know if one of them is bigger or less than the other, right? Because when you do a 90% confidence interval, if this was the real number, let's say it was 4, that would mean the first is bigger than the second. But couldn't it also be -4, which would be the exact opposite conclusion, right? And you don't know which one of these numbers is the right one. All you know for sure is that it's somewhere in that interval, at least 90% of the time. Are we comfortable about how you can take the interval, right, and make conclusions about the population means bigger than, less than, or you can't tell? So let's show you, because this section is actually pretty quick because of the fact that most of the heavy lifting is actually being done by SALT. So here is, there are two, is this number 1 or 2? Yeah, this is number 1. Okay, good. There are two questions, the first two, which are basically identical in a lot of ways. Right. And right, so back to question 1. Here is a story about how scientists, how archaeologists at least, go about looking for places. Let's say you're looking for grave sites, right? Ancient grave sites. One of the ways you can do it is by taking samples of the phosphorus level of the ground. Didn't know that until I read this question. And evidently, if you take phosphorus, most natural things, right? Plants have phosphorus in them, right? And depending on how much phosphorus, there's a kind of hierarchy. So fruit have the lowest, vegetables are next, cereals are next, nuts are next. And when I first read it, I said corpse. That's my reaction. And corpses, i.e. us when we die, have a lot of phosphorus in us, evidently. So what they do is they collect samples from a region and then another region, and they're interested in phosphorus content. And if you have a really high phosphorus content, you might have found a graveyard, right? Lots of dead bodies, lots of phosphorus, right? So if you're wondering how they could tell, you know, there's a very simple way, right? Take some little soil samples, figure out how much phosphorus, and see if it's interesting. So we have two regions. They have one region 1 where they took 12 soil samples, and these are the numbers. And then you have region 2 where they have 16 of them, and they got these. And they are interested in phosphorus content. So that's what these numbers represent. So I'm going to hit use salt. Okay, this is dangerous. Hit the button. Oh, good, I've got the question. Right, now, if you hit the salt button and you go to inferential statistics, go over here and pick 2 sample T. Right, so pick 2 sample T because there's 2 populations, right? 2 samples. Select the variable, region 1 phosphorus. Select the variable, region 2 phosphorus. So far, so good. So this is us telling SALT where the data is, right? The first population is site 1. The second population was phosphorus levels in site 2. So far, so good. Now, we are interested in a confidence interval. And I have no idea what that question wanted. So, oh God, yeah, they did. Okay, I'm doing it only because they made me do it. 80% confidence interval, right? You know, if you do that, you're going to be digging in the wrong place 1 in 5 times, aren't you? So you have a lot of money or a lot of time. I wouldn't want 80% on anybody, right? Now, they've got this little thing here called assume equal variance. You would look at that and say, well, what does that mean? There is a tweak to the way salt works. If you can make the assumption, and it's a reasonable assumption, that although I don't know what the standard deviation is, I'm pretty sure they're the same thing, then you will hit assume equal variance. That is very unlikely to be the case. I mean, you might get away with it sometimes. You know, you might say, well, I don't know what the standard deviation of females and males are, but I'm pretty sure they're about the same. You would hit the equal variance. So my suggestion for you is not to hit that button, right? Just leave it blank all the time. If you don't get an interval that works, then hit that button and try it again, and you should get one that does work. Because it's not always clear, to me at least, when they say it's got equal variance. You might not know it until after you've done all the number crunching. So anyway, generate results. Now, in this particular one, we have mean and standard deviation of the first group, and we have mean and standard deviation of the second. So now I'm going to use this data. Do you see that guy there and that guy there? Would you agree that those standard deviations are quite different? They're not very close to each other. So I was correct in not checking that box. Can you think of this might have been 170 and this one was, I don't know, 172, just for argument's sake. Then I might go back and say, oh, okay, it looks like based on the information, the assumed equal variance would work, right? So if you want to say, well, how do I know? Do you know you don't really know until you've committed and you've hit the button and you see the data? So in this question, we've got all these numbers, and I'm now going to pull this out over here, and they want to know the mean of the first group. So I'm copying and pasting it, and it goes in here. And you want to know the standard deviation of it. Basically, just copy and paste. And paste. And then you go and you do the mean of the other group. And then standard deviation. And I've already got those two guys in, and I've checked them. So I knew I was correct. So here, maybe I should make this a little bit bigger. There. Now, can you see the lower limit is negative 86 and the upper limit in this case is 103.7? Do you see that? Right. Isn't that interval got negative and positive numbers in it? So what that is telling me is that I can't tell any statistical difference between the two populations' phosphorus content. So my conclusion would be, I can't tell you which one of those sites is more likely to have burials in it, right? The two are very similar. Can we pretend for a minute that that number there was positive 86, just for argument's sake, right? So the difference between them was 86 to 103. Can you imagine that being the interval? Now, aren't all of those positive? Right? And if you're positive, doesn't that mean the first population mean is bigger than the second? So if I had to go digging for bodies, wouldn't the first site be my best candidate? Right? It's got much higher phosphorus than the other. But in the answer that we got, which is this one, because the interval contains both positive and numbers, we can't really say that one is more interesting than the other. Right? And then it hits you with this guy. And it says, which distribution, standard, normal, or student T, should you use? And you are going to answer that one every single time, because there are no questions that we've got where we know the standard deviation of the population, right? We don't know sigma 1 and sigma 2, because these questions are all based on samples. So in a way, that question's kind of stupid because it's the same answer every time, right? At least the ones you're going to see. Are you comfortable about how I use salt? Right? Okay. Let's move on to, are we okay with that? You want to see the buttons again? You're going to see it when I hit the next question, but you want to see this one again. Okay, don't have any great desire. This one here is very similar to question 1. So stand by it. Right. Next question. For large American companies, what percentage of their total income comes from foreign sales? A random sample of technology companies like IBM and Intel, those kind of places, gave us the following information. So here is 16 major companies, and this is the percentage of foreign revenue. That's kind of interesting. Do you notice that quite a lot of them, it's even more than half their money comes from selling it to France and Germany, and who knows, we may even sell stuff to China, right? Occasionally. So we have a lot, our tech companies are heavily dependent, aren't they, on selling their stuff to Europe and Africa and Asia and whatever. Interesting, that. And that's for technology. Now, another independent random sample of basic consumer products. Goodyear, what's tires, cakes, baked beans, toys, right? So things you would probably buy every day, right? Or, you know, at least reasonably often, and they tend to wear out, right? So you consume them. I guess that's why it's called consumer products, right? If you're anything like my nieces, do you know if you give them a toy, if it's alive in 6 months, it's a miracle? Leanna, you've got kids. What's the average life expectancy of a toy for one of your kids?
Right now, he's not that hard on his toys, but if he breaks them, I throw them away. So he hasn't broke one in a really, really, really long time. His friend broke it before he broke it.
Okay. You've got a good kid. I wasn't too bad, but my brother David never kept a toy because he was always interested in what made them work. So he always dismantled them. So he had enough knowledge to dismantle them, but not enough knowledge to put them back together again.
That's where we're kind of they have these toys now where it's like it comes in a million pieces and they give you stuff to like build the toy. So I buy him those where he like has to like put the screwdriver together and then like screw the toy together. So he made a little truck recently. So he has like a whole bunch of those around. So I'm like, cool, build things and like destroy them instead. So that's kind of where we're at.
Okay, I got you. Now, what they're looking at here is there a difference between companies, tech companies, and the percentage that they sell and consumer? Now, if you just look at the raw data, would you say that there's a pretty significant difference? Would you agree these are much higher than consumers? Just looking at one for one kind of thing, right? So we're going to try and structure that statistically. In other words, we're going to find a confidence interval. And if the confidence interval has nothing but plus numbers, isn't that evidence that this is bigger than that? And if the interval has nothing but negative numbers, which I strongly suspect won't happen, this will be smaller than that. And if they have plus and minus, you might think there's a difference, but statistically, there's not enough evidence to prove it, right? So don't, sell your house and bet on it. So once you've got the basics, you're going to do the same thing pretty much for every one of, I think it's the 5 questions that you've got, or 7. You hit the salt button. Now, can anybody remember which one of the headings along the top is the next place to go? Because we're going to do it the same way each time.
IS, the inferential statistics.
Looks good. Now, when you hit inferential statistics, it would be nice if they set it up for you, right? It would have been nice, but they don't. So now we have to kind of, jog it along a little bit by helping. So the next place is one sample T. Now, when I click on this, I've got a whole load of choices, but which is the only one I should pick in this context?
The 2 sample. T.
Now, what? Yeah. Now, when you do that, do you notice that some of the things have now changed? Right? You've got some extra things. You've got a sample 1, Well, if I click on that, won't I make that technology? And then sample to basic consumer. Do you see we tell it who one is and who two is? You would think it would be clever enough to know that, but we have to tell it, right? I'm going to make an assumption, as I do for every question, that assume equal variances is left blank, right? There's no way in the world I could make a reasonable conclusion that the two populations have the same variance, right? I don't see any evidence of that, so I'm not going to click on it. And I've forgotten which one we're going for, so please don't be 80%, or you'll make me a liar. Yay! And 95%, a sensible one. Okay, so let's click on it. Confidence interval 95, generate the results. Now, mean standard deviation, good to go. The intervals are 10 and a bit to 25 and a bit. So I'm just going to call it 10.7 and write that down. I'm going to call it 10.7 and 25.4. So let's go back in. 10.7 and 25.4. Right, conclusion. The difference between electronics, right, and consumer goods, right? Tech and consumer. Would you agree that the difference is positive 10.7 to positive 25.4, right? And all of those positive. So shouldn't we be able to come up with a conclusion that because the interval contains only positive numbers, we can say that technology companies have a higher percentage of foreign revenue? Click on it, and that would be the correct conclusion. Now, if you wanted to push it a little bit, couldn't we even say something like, not only do technology companies sell more to foreign countries, on average, don't they sell about 10% more? At least 10% more. Now, the reason I can say at least 10% more is, do you see that guy there is 10.7? Right, that's the worst case scenario. They're still going to be 10% bigger and a bit more, right, than the other. So when you can imagine people analyzing this, you know, people are into the stock exchange, right? So if I'm in the stock exchange, which actually I'm not because I'm too sensible to be in it right now. It was a really good idea to get out of the stock exchange last year. I wish I'd done that, but I did get out of it early enough not to lose all my money, so I'm kind of happy about that. If you're into the stock exchange and you notice that, if you know anything about the world's economies right now, everywhere, including America, is having a hard time, right? But Europe is having a much harder time than we are, right? So if I had to buy stocks, I would get out of technology right now. Sell anything that's technology. Why? Because if they sell most of the stuff to France and Germany and, you know, places like that, and these are the countries that have a hard time, won't they buy less technology off you? So those companies are going to have their profit margin hit. Whereas your kid's still going to get toys, Leanna, right? And he's still going to get baked beans, and he's still, your tires, you're going to have to buy tires when your car gets a flat, right? So,
Yeah.
so those companies, aren't they going to survive a little bit better in a bad economy? You're not selling so much to foreign countries, and you're selling stuff that people kind of have to buy, right? So being food, being consumer goods, that would be my advice. But don't go into stocks at all would be my real advice. But if you had to, that's what you would get. Now, you see how you can actually base that on good data. If you've got good data, you can actually make pretty reasonable decisions. Right? They have a fancy jargon name for that in business. It's called evidence-based decisions. So you don't do gut feelings, and you don't do anything to do feelings. You do it straight from data, right? What is the data telling me? Off you go. Now, if we're doing the medical one, right? Let's suppose we're doing a medical one. I know these numbers are not medical, but if they were, couldn't one group be the blood pressure of people getting the old medicine, and couldn't the second population be people getting the new medicine? then wouldn't you be interested in the difference in the blood pressure? Because wouldn't that tell you which medication was doing a better job than the other? Do you see how the difference would help? So you can use this comparison technique for anything that involves two populations that you want to compare. So it's pretty powerful. Plus, if it says it's pluses, you're 90% sure, or 99 if you really want to be sure. Sure, right? Now, next one. Independent random sample. Oh, good, they're picking the football players. An independent random sample of professional football and basketball players gave the following information. Assume that the weight distributions are mound shape and symmetric. Okay. Didn't need that, but it's nice. I wonder if they're mentioning that because they're trying to say, hey, it's probably equal variance. I think that might be code for equal variance. I'll find out. Now, if you look at 21 football players, here is their weight. And if you look at 19 basketball players, here is their weight. Looking at raw data, do you think there's any difference between the two groups, basketball against football player? Aidan, what do you think's the heaviest?
The football players.
Right. If you watch, which I do, football, would you agree that there are a lot of big, heavy duty guys? Now, they're not all heavy duty. Don't you get the guys that, I forgot the names of them, although I like the sport. You know the guy that throws a ball, right? The quarterback. They tend to be not as big as the guys in front of them that are protecting them, right? They might be half the size of them, right, weight-wise. What's the guy, the running back, right? Don't they have to be smaller and therefore lighter? But in general, isn't the average weight of a football player much bigger? On the other hand, aren't basketball players basically not that much different on positions? Aren't they all tall is more important than almost anything else? So I would go with that. So we are about to find out. You saw. Go to inferential statistics. I'm doing the same thing every time, two. And the first one's going to be football players, right? And the second one is going to be basketball players. I've forgotten what they want this time. What kind of... Somewhere in here, there's going to be a confidence interval, isn't there? 99, good. And we are going to do confidence interval 99. And I'm not going to hit that for a minute. I'm going to generate results. Oh, okay. Do you see those two standard deviations? I know they're not identical. They're never going to be perfect because it's samples. But would you agree they're close enough to probably make that a reasonable assumption? Right. And all you do, if you think that's the case, is just click it and generate the results. And I think I've generated them. I have, right? You won't notice a lot of difference, but there will be a little. You know how that's 43 and 64? It might have been 42 and 67, right? The other way, right? So there'll be a little difference, but not a lot. Would you agree that it's somewhere between 43 and 64 is the difference? So aren't football players bigger than basketball players weight-wise? Probably by at least, on average, 40 pounds. If you're really pushing it, on average, 43 pounds, right? If you're cutting it to the edge. And that's provable. In other words, every statistician who looked at the same data would come to the same conclusion, right? So we don't have that interpretation thing, which I love, because the minute you have interpretation, can't A be B and B be A and up can be down, and nobody agrees on anything, right? So we have formalized this. Is you want to check the difference between two populations, use the t distribution, which is what this program is doing. Come up with an interval. If your interval has got nothing but positive numbers in it, you have now proved that the first population mean is bigger than the second. That's it. Drop the mic, walk out the building. It's done, right? If the intervals are two negative numbers, haven't you proved that the first population has a mean that's smaller than the second? That's also true. And if you get an interval that has positive and negative numbers in it, the answer is, we don't know yet. Could be one, could be the other. Can't tell you. No evidence one way or the other.
I have a question. At what point would you click that little box versus not clicking that little box?
Or the assume
Yeah.
equal variance.
Yeah.
I would never click it unless they gave me a clue in the question. Because
Okay.
there's really no way of knowing. How can you know if the standard deviation of two populations have an equal variance when you don't know really anything about them?
Okay.
I think their clue in the sentence, which ended up being correct, was assume that the distribution are mound shape and symmetric. I think that's them saying, you know, I wish they'd just said, assume that they had equal variance, because
Okay.
then you wouldn't need to decide.
Okay.
It's when you're doing your homework, if the first one doesn't work, well, you click the box and the second one will. And since you get 5 guesses, it's not going to be a big deal, right? In the final exam, for instance, I would know what both answers were, so I would be able to, I'd fix it even if Web of Science said you were wrong. You know, when you do tests and that doesn't tell you whether you're right or wrong, right? But I would fix it.
Okay. Thanks.
Okay. What's this next one? Right, we got 2 more to do. What's this data about? Oh, that's another football player one, so I'm not doing that one because we've done one like that. And this one I think is our last one, so let's do this one then. The following data represents petal lengths in independent samples of 2 species of iris. God, that's a boring story. But anyway, you've got 2 versions of an iris plant, right? 2 species, you know, the red iris and the green iris, whatever they're called. And you've measured their petal length because you have no life and you're just interested. And you've collected 36 of the first one. Here are the petal samples. And 38 of the second one. Here are the petal samples. And just looking at that data, would you agree that the first population is bigger than the second? Just looking at raw data. Right, can you see a lot of 4s and 5s and a lot of 1s? I'm 99.9% sure we are going to get an interval that has a positive value in it. So let's see what we get here. Now, it says here, use your calculator. That's not really true. You're going to use salt. You're going to go inferential. 2 sample. First kind of iris. Second kind of iris. I'm going to make the assumption to leave that blank. Confidence interval. And this time they want a 99, which is fine by me. Nice sensible number. And I'm going to generate the results. And it's somewhere between what, 3.7 and what, and 4.3. Is that clear evidence that the first petal is bigger, the first iris has bigger petals than the second one? Are we good with this process? Because most of the number crunching is done by Salt. And although the stories changed, didn't the method look almost identical? Couldn't I have just left out the story and you would have came up with the same conclusions? First guy's bigger than second, first guy's less than second, or you can't tell. That's your conclusions. Any questions before we leave this? Because that's the end of that topic. Last chance. Are we good? Okay. Let's start our next topic. We are now going to look at estimating a single population proportion. And then we're going to do the difference between 2 proportions. So it's almost exactly what we did there, isn't it? Single mean, difference in 2 means. Single proportion, and then tomorrow, difference in 2 proportions. So let's give you the first one, right? Single proportion. We are going to do these guys by hand. In other words, we're going to have a formula that we can use and we'll calculate them. So let's give you a story behind it. You have a population. And this population is going to be Scottish people, because I want it to be. And you went and asked, pick a sample. You asked a sample of 200 Scotsmen. How many of them had been drunk in the last week? Right? And we use this notation. You see that P with a little hat? You call that P hat when you say it out loud. And that's the proportion, right? So the proportion of Scots guys who went and said that they were drunk, let's say it was 95 of them, right? 95 out of 200 Scottish adults said that they were drunk. And I'll turn that into a decimal now. And typically you work with decimals in these questions. So I know that the question is going to be like 80 out of 200, 50 out of 103, that kind of thing. But turn them into decimals is just helpful for the calculation. And we are going to create a 90, a 95, or a 99% confidence interval using just this data. So here we go. The 90% confidence interval. It's going to be P hat plus or minus 0.164 times the standard error of P hat. It's P hat plus or minus 1.645 times. Now to get the standard error, you do this guy. So the standard error is this calculation. Right, now it's plug and chug. I want a 90%. Oh, do you know why it's 1.645? Can you remember where that magic number came from?
Were they the three scores that you're supposed to use to calculate with?
Yep. So 1.645, I'll put it over here. If you want a 90%, they called it ZC, right? It was 1.645, right? Anybody remember what the magic number for a 95% confidence interval was? .645 got you a 90. What number got you a 95? Because that's the only thing that changes, right? That'll change to this next number. Last chance.
1.96.
You nailed it. And what's 99% going to get you?
Isn't it like 2.65 or something?
Pretty close,
2.5.
2.58. A pretty good guess. Right. And, you know, that should be written down somewhere, especially this week, right? Because you're going to refer to it from time to time. Right, now back to our calculation. It's P hat plus or minus 1.645 times the square root. P hat is this guy, right? So it's 0.475 times 1 minus P hat is 1, take away that guy. So that's 0.525. All divided by 200. Now I know what P hat is, it's 0.475, give or take that. And the good news is that as ugly as that looks, you can actually do it in one go in your calculator. So here goes, 1.645 times the square root of 0.475 times 0.525 divided by 200. And the answer I get is roughly 0.058. Are you comfortable with the calculation where it came from? So if you want a 90% confidence interval, use this formula. P hat is this guy here. N is the sample size. And then all of this stuff here, right, gets multiplied together, gives me that. And P hat goes here. And then all you do is take that away and add it. So let's take it away first. So if you go 0.475, take away 0.058, oops, try that again. You get 0.417. I believe they call that the lower limit. And then if you add it, 0.475, add 0.058, you get 0.533. And that's called the upper limit. So our 90% confidence interval for the percentage of all Scotsmen, adults, who are going to be drunk in any given week is somewhere between these two numbers, right? So what would that be? On the low end, it's about what, 42%. On the high end, it's about 53%. You see, we've got our interval from here to here. Are we good? Now, we have some names. Do you see this guy here, this piece here? It's 3 words. What name do we give to the 0.058? Margin? Two more words to go.
Over here.
Of error. Are we good? Margin of error. So that's our point estimate, and this is our margin of error, right? And anywhere between these two numbers is just as likely to be the true answer as any other. So that 0.475 is nothing special. It's one of possible answers. Couldn't it be 0.5? Couldn't it be 0.433, right? Couldn't it be any number up to what, 0.533, right? Any value is possible for the real population proportion value. So let's do an election one, a pretend one. You don't know this because I've made this up, but there is a Royalist party in Bremerton, and I'm the candidate for it. And I want to become the next mayor of Bremerton. And so they're conducting a poll to see what my chances are. And they asked 1,003 likely voters. That's people who said, yeah, I'm probably going to vote, you know, in the election, likely voters. And there are 1,003 of them. And in that 1,003, 549 of them said they were going to vote for the Royalist Party. So let's see what that looks like. 549 divided by 1,003, and the answer is 0.547. Let's just say to 2 decimal places, right? So it's 0.55, or essentially 55% of the vote, right? Now, if that's all that was being used, couldn't I have on the local radio, Professor Robertson is going to win the Bremerton mayor's race, and there's now going to be a Royalist in power? But technically speaking, isn't 55% of the vote going to win you the election, right? In fact, to win an election, don't you just need 50% plus one more person? Right? That'll get you the election. So yeah, at least superficially. But that was only based on a sample. Couldn't I take another sample of 1,003 and I would probably get a different answer, right? And couldn't I get an answer that might be 49.8%, in which case I lost the election? We'll assume it's only a two-party race, right? Me and somebody else. So you can't say for sure, based on a point estimate, anything. Couldn't I just be an unusually big number or an unusually small number, right? We can't base it on that. So we have to do the whole thing. What do you want? A 90, a 95, or a 99% confidence interval on this data? What are you looking for? Pick it.
Let's do 99.
Okay. Now, if you're going to do a 99% confidence interval, if I end up proving that I'm going to win, couldn't you go to a gambling place and bet some money and probably get, you know, make a little bit of money on the side, right? Okay. Not that you should gamble, but if you did. So the formula is P hat plus or minus. I'm going to keep plugging this as much time as I have so that it'll stick in your brain. What is the magic number for a 99% confidence interval?
2.58.
Correct. Right, so that's basically the generic formula, right, without too much detail. Now we know this guy, so I'll put him in as 0.55. It's going to be 2.58, and then it's P hat 1 minus P hat all over n. So it's going to be 0.55 plus or minus 2.58 times, you probably don't need every single line that I've got here. If this is 0.55, isn't this guy one takeaway 0.55? So that's where this answer came from, right? 1 subtract this guy gets you that guy. All over 1003. So I'm going to multiply them together and get the margin of error. And the answer is 2.58 times the square root of 0.55 times 0.45 divided by 1003. And the answer I get is 0.04, roughly. Agreed? 0.04. So if you take that away, you got 0.51. If you add it, you get 0.59. Okay, so there's my 99% confidence interval. I like percentages, so 51% to 59% are going to vote for me. Right? And I'm 99% sure that 51% to 59% are going to vote for me. Wouldn't the conclusion be that the prediction is that I'm going to win the election, even though it hasn't happened yet? Great. And if you are doing that on the local radio show, shouldn't you say margin of error is plus or minus 4%? Have you ever heard them say margin of error plus or minus 2%, plus or minus 4%? Next time you watch the TV and they're talking about polls, they should, if they're being honest and fair, tell you the margin of error, because doesn't that give you a kind of idea of accuracy, right? Can you see in this case, margin of error is 4%? That's where this came from. So they would probably say it like this. 55% are going to vote for the Royalists with a margin of error of 4%. That's how it tends to appear on TVs, isn't it? You ever seen things? You ever wondered where that margin of error came from? Do you now know? Kind of cool. Now, if I had said to you, 55% are going to vote Royalist, and the margin of error was 10%. If you don't know how to interpret this, aren't you still going to think the Royalist is guaranteed to win? But if you convert that into an interval, isn't that 45% to 65%? Right? Give or take 10%. Now, if you look at that, couldn't I easily lose? Couldn't I only get 45% to vote or 49%? I'd still lose. And isn't every single one of the numbers in that interval just as likely as any of the others? Do you see why not telling someone the margin of error could be a way of giving false impressions, right? If I just told you that 55%, you would think quite naturally, hey, that guy's likely to win. Now I've told you that margin of error, aren't you still going to say, yeah, he's going to win? It could be a close call, right? He could only get 51%, but he'll probably win, right? If I told you that, shouldn't the conclusion be nobody knows, the game is up in the air, anybody could win? So I'm picking on Zach. Zach, you're about to vote maybe next week, and the results came in from a poll, and the guy you don't want to win, that's me, because you're not a royalist, right, has 55% of the vote. That's all they tell you. And the weather is horrible, and it's pissing down rain that day, and you've got the kids to pick up, and you've had a hard day at work. Are you maybe likely to say, oh, what the heck, the other guy's going to win, why should I bother?
Absolutely.
Right?
Hell yeah.
Now, if you look at this data, hey, my guy could win. Aren't you likely maybe to say, what the heck, I've got a chance, I'm going to go and vote? That is a technique that they call suppression of the vote. Politicians do it a lot. It's not illegal, but you can see how they can make you be more or less interested in voting, right? They want their guy to be energized. They want people to come out and vote for your guy and not for the other guy, right? And so what kind of tricks do they do? Obviously, they do this type of trick, but don't they also throw in last-minute surprises? Like, oh, there's a rumor that candidate Robertson has been taking bribes from his students to pass exams. Now, we've no evidence of it, but we do think there's a lot to be said for it. Can you see that after the election, those rumors were totally unfounded? But haven't I lost the election? Do you see how dirty they can be? So my advice to you is, I don't care who you vote for. It's nothing to do with me. It's your own personal preference. But if vote for the person, pay no attention to the polls. They can be, doctors in a way that puts you off. Right? And unless you see a picture of your candidate murdering a child and then eating it, pay no attention to the stories that they'll make about that person before the election. Because so many of them don't come to fruition. So that's my advice. Don't care who you vote for, just vote. That's the biggest way to screw up democracies, is by doing that to you. And there, I've got that little thing out of my system, so I feel better. And you are all going to vote in the coming up elections, right? All of, right? Aidan,
Already sent ours in.
right? Aidan, remember to vote early and vote often, okay? Oh, you didn't get that joke. Did anybody get that joke? Remember to vote and vote often, right? No? Okay. Do you know that if you're dead, you're still allowed to vote?
Isn't it for 1 year? For the year of your death, your spouse is allowed to vote for you.
I don't know. God, now that you've told me that, I didn't know that. I was just going to crack a joke and saying in Chicago, dead people vote all the time.
I think that is the case. I think if you pass away in that year, your spouse can vote for you.
Yeah, but your spouse might not be politically on the same side that you are. I guess it, yeah, could happen. Okay. Back to, I guess, the storyline here. Are we good with these guys then, right? So let's do one more, and then I'll kind of have to close this thing off. I've got lots of windows in my way. Let me. Well, actually, now I'm thinking about it, let me do one of their questions, because you know they do things their own unique way. Right, waiting for something to open. Right. So, question 2. A random sample of huge number, 5,427. That is typically a really big sample. Do you know the ones that we're talking about, the politics ones? They're almost always like 1,004, 1,012. That's the kind of size. They're almost, or at least the honest ones, are done by companies like Gallup Poll and so on. And I guess the reason it's 1,000 and change is, you know, some people will say it's none of your business, and so you don't get, you know, you're trying to make sure you get at least 1,000 answers. Now, in this particular one of 5,427 physicians in Colorado, 2,954 provided some charity work. So they would take patients in and not charge them any money. I'm assuming that they have to pay for any prescriptions, but at least they get the doctor's visit for free. And 2,954 out of that sample in Colorado and provided some pro bono work, which is nice of them. And I'm now turning that into a decimal. And I'm following their instructions. And their instructions is that they want at least 4 digits after the decimal point. So I'm going to do one more for luck. So if they say do the answer to 2 decimal places, well, you do all your calculations to like 3 or 4, and only when you're finished, the last answer, round it off to 2 if that's what they want, or in this case 4. So that's why that's got 5 decimals. And the reason you do that is if you do a calculation to 4 decimal places, won't rounding off sometimes accumulate, and so your answer might be just a little bit out because of that. So it's just for accuracy. And we are being asked essentially to find a 99% confidence interval. And so that's going to be p hat plus or minus 2.58 times the standard error. That's going to be 0.54432 plus or minus 2.58. Instead of writing the formula down, I'm just going to write P. 1 minus p hat, which is 0.45568, all divided by 5,427. I expect this margin of error to be tiny. And the only reason I can say that with some degree of certainty is, isn't this number really big? And if you divide by a big number, don't you get a small answer? So big samples, small margin of error. That's essentially what that's saying. So it's now going to be 0.54432 plus or minus whatever the calculator tells me that is. So here we go. 2.58 times a really long decimal calculation, 0.54432 times 0.45568 divided by 5427 and 0.01744. And take it away and let's see what we get. So 0.54432. Take away that guy. So this number, I'm now going to round off to 4 decimal places. And then I'm going to add them. So 0.54432, add that guy. And This guy gets rounded off. Right. Now, if I had stuck to that number, right, the 3 instead of the 3-2, this answer here would have been a little bit different. It might have been 6-7 or 7-1. It might have been 1-9 or 1-4, right? And you know, WebAssign can be very, very pernickety, can't it? Even a 0.01 out, it'll say you're wrong. So just to be in the safe side, that's why I'm doing that. Now, lower limit would be this number, upper limit would be that one, and we're pretty much done. Right? What could I say? Would you agree that there's evidence that more than half of the physicians do pro bono work, right? In fact, you could say at least 52%, right? 52% or more, for sure. Now, when can you actually do this? Well, the first thing is that your sample has to be large. And we all know is how long is a piece of string is very vague. So there is a test for it. When you were doing means, wasn't large 30 or more, right? Wasn't that the go-to number? Most people agree. There is a little bit of variation on that one because some people will do it with 17 because that's all the ducks they've got. Remember the story? Sometimes you can only do, you know, you've only got so much numbers, so you kind of bend the rules. You shouldn't really bend the rules with this one because they have a test for it. Large means that n times p hat has to be bigger than 10 and n times 1 minus p hat must be bigger than 10. It's very often called the 10 rule for pretty obvious reasons. Now, if you want to know what that calculation is, it's basically that number times this guy, right? N is 5427 and p hat is this. So if you multiply that by that, is your answer bigger than 10? There is an easier way to actually figure this out. And it is the number of people who said yes to your question has to be at least 10 people. And the number of people who said no to your question has to be at least 10. Would you agree that if 2,900 said yes, there's probably another 1,300 that said no, but aren't both of those bigger than 10? And that's the easy way to check it, right? So if you only had, oh, let's pick one where that's not true. Let's suppose that you asked 20 people a question, whatever that question might be, and 50 of them said, yes, I like Pepsi, right? Then won't 1 minus p hat be 5 out of 20? Agreed? Now, in this question, 15 said yes, but only 5 people said no. You shouldn't use that sample then. It's considered too small. Not because that number is 20, right? That wasn't the problem. Wasn't it because this number was 5? Now, you could even have a big sample, say 100. And the number of people who had a particular genetic disease was 4 out of 100. And the number who, you know, the proportion who didn't have it was this guy. Well, wouldn't the yeses here be 4 and the no's here be 96? Wouldn't you fail it again? So a sample size has to be large doesn't really mean this has to be large. Doesn't the yeses and the no's have to be at least 10? That makes sense, but that's the rule, right? And everybody has agreed on it. And the second one is that it's a random sample.
So
And the
are you
third
saying
one,
that I shouldn't trust all of those commercials saying that 4 out of 5 dentists think that this toothpaste is good?
if only asked 5 dentists, yes, don't pay attention to it. But couldn't that data come from 500 dentists? and 400 said they like it. In that case, it would be legal, to say it, right? Now, random sample, we assume that the people in your sample are a fair representation, and then ask the question, for want of a better word, fairly. It's bad phrasing, but I'll tell you. Right, random sample. If I pick 100 people, isn't it a good idea that the 100 voters I pick are old and young and rich and poor and heavy into politics and don't really pay much attention, right? A good spread of the entire population. That's what a random sample should be like, right? Wouldn't a random sample not be random if I only went to, I don't know, went to a protest meeting and asked 1,000 people at that protest meeting their politics? And wouldn't I get a very strongly biased sample depending on what they were complaining about, right? And ask the question fairly, yeah. Don't say to people, are you in favor of killing an unborn child if you're interested in abortions? Would you agree that is a very biased way of asking, are you in favor or against abortions, right? So be careful about how you ask your question and make sure that it's random. Now, there's lots of other things that are going to happen, but that's for a different section. But this one here, the 10 rule, is one that we should be aware of, right? Because that one will get tested. You can't really tell in the questions you're going to see if these two things have happened. We just assume that they are okay. So let's try another one. This is a version of question 3 about politicians. A random sample of 60 professional actors found out that 36 of them were extroverts. Okay, now let's do the test on that. You should be able to do that right off my bat. Would you agree that the yeses were 36 and won't the no's be the other 24? Wouldn't that be the 10 test without doing the calculations, right? So I know I can do it. Now, you want to do a 95, a 99, what do they want? They want a 95, okay. So a 95% confidence interval based on this would be p hat plus or minus 1.96 times the standard error. That's going to be 0.6 plus or minus this guy. And again, I'm just going to do the calculation. P hat 1 minus p hat over n. So 1.96 times square root 0.6 times 0.4 divided by 60, and the answer is, what accuracy they want in here? 4 decimal places. So give or take 0.1236, yeah, 1 for extra. Now you take that away from that, you get 0. What do you get? 0.5. No, you don't. You get 0.4766, and you get 0.612396. I should have rounded that off. 4760 and 0.6124. I believe that sounds it. So somewhere between 47 and 60, let's just make it really very round numbers. So somewhere in that range are extroverts. So here's a question for you. Based on this small sample and this 95% confidence interval, would it be fair to say that more than half of professional actors are extroverts? Would it be fair to say more than half? No. because couldn't it be 47%, which is less than half? Couldn't it be 48 and 49, also less than half? Remember, any number in the interval is just as likely to be the true answer as not. So this is not evidence that the majority of actors are extroverts, right? Now, if I did a different one and I got 53% to 68%, let's suppose I got that interval, wouldn't I then be able to say, yes, there's evidence that the majority of actors are extroverts, right? Bigger than 50% is majority. And if I got that interval, couldn't I say that there's evidence to prove that less than 50% of actors are in fact extroverts? My own gut feeling, totally gut feeling, no evidence, is I think actors probably are extroverts in general. I think there's always exceptions. Because wouldn't you have to be a bit of a show off to be an actor? Because what actors do, right? Just gut feeling. Who knows? Anybody know any actors? Because I don't. No. The ones I do know in the sense that I see on TV, I always think a lot of them are very big-headed. Right? They think a lot of themselves. I've played a doctor, so I can now tell you how to live your life medically. Right? I played the president, so I can now tell you how the country should be run. Right? I fought in a pretend battle, so I know everything about the Ukraine war now. But maybe that's me. I think actors are very extrovert. They think a lot of themselves, in my opinion. What do I know? I think we get time for one last one. I'm just trying to find a question. These are all homework questions, so I've done that one. I don't want to do that one again. Is there anything in here that's interesting? Oh, there is. Okay, I'm not going to do one of their questions. I'm going to do one of my own. And it's not one of these guys. It's a different kind of question. I would like the margin of error to be, oh, I don't know. I would like the margin of error to be 2%. How big should my sample be? Interesting question, right? Right, I'm going to conduct, I haven't done it yet, right? I'm going to conduct a survey to see if the Royalists are going to win Bremerton, right? And I'd like the margin of error to be 2%, right? Plus or minus 2%. How many people should you need to ask for that to happen? Let me, oh, I need to tell you a certain level. So which one do you want? 90, 95, or 99?
Let's do 95.
Okay, let's do. So I would like it to be 95. So there is a formula. I'm looking for the way they've written it, so I don't end up writing, my version of that same formula down. The margin of error is given by, for a 95%er, it's given as 1.96 times the square root of p hat, 1 take away p hat, over n. Right? Now, if you know what p hat is, you have to plug in the number, but your chances are you won't know what the p hat is. So it's going to be 1.96 times the square root of a half, take away a half, right? That guy. And I want the margin of error to be 2%. And that's a half times a half, so that's 0.25 over n. Right. And here is one of the few times you're going to get an equation. So I've basically put in everything I know the value of. Now, if they tell me p hat and 1 minus p hat, I'll put those numbers in here. If they don't tell you, always pick 0.5s. Right? That's the worst case scenario. Now, it's been a while since you had to solve equations, but as long as you do it to both sides, it's okay. Any suggestion for what I might do to both sides to get closer to finding n? If I cover that up, there's a clue. Last chance. Okay, here goes. Divide both sides by 1.96. So on my calculator, 0.2 divided by 1.96. Try that again. 0.02 divided by 1.96. And the answer I get is 0.010. And it has to equal this guy. And by the way, when I'm finished this, I'm going to show you another formula, but this is me showing you where it comes from. Right, any suggestions what I might do to both sides? Next, think of algebra and solving equations. I want to find n, but what should I do to both sides first?
Square it, get rid of the square root.
You are right. So 0.01 times 0.01, and I now get 0.1231. It looks like that, but that's what it is. And now I have this guy. And if you do a little over 1 and you cross multiply, you now get this guy. And if you want n, you now do that guy. And that ends up being 0.2, oops, clear it out, 0.25 divided by 0.0001. And the answer to that then is 2,500. So if you want to get a 2% margin of error with a confidence level of 95%, you need to do 2,500 people in your sample.